the computers used by IBM and other companies like Google are very interesting, look like this strange device that we can see here, where most of the cables and the devices that you see are not really the qubits or the quantum processor in itself. For this technology to work, we need to keep the temperature of the chip close to absolute zero. Okay, so most of these things that you see here are devices that are used to keep the temperature very low, and also to control the behavior of the quantum chip, which is just at the bottom of all these devices. And when it works, this cylinder here closes completely. You need to have this chip completely isolated from the environment. We will see that noise and interference with the environment is very dangerous for quantum computing, because the properties of these quantum bits are easily destroyed. And this is just how the computer looks when it is open. When it is working, you only see this cylinder. You may think that working with these quantum computers is very expensive, and it's only possible if you work at one of these companies or at research laboratories that work with these quantum devices. But since 3 or 4 years ago, we have the opportunity of interacting with some of these quantum computers for free. So, for instance, IBM and other companies, including, for instance, D-Wave, a Canadian company, offer the possibility of accessing these quantum devices for free. So you can just log into these web sites, create an account, and you can start using some of these quantum computers. Not the most powerful ones, but they are quite interesting, and you can use them to start learning about how to program these quantum computers. And there are many different quantum programming languages that have been developed in the last few years. Here I have listed some of them, for instance, Qiskit or Cirq, which is developed by Google. And most of them are focused on the task of designing quantum circuits. If you remember, I mentioned that this circuit model in quantum computing is one of the most popular, probably the most popular nowadays. And most of these quantum programming languages are focused on how to specify the different elements of these quantum circuits in order to execute quantum programs in the quantum devices. And the elements that are important in this model of quantum circuits have an equivalence in the classical realm. So when we think about an algorithm, we always have 3 elements. We have data, we have operations that we perform on this data, and then we have some results at the end. And each of these elements has an equivalence in the model of quantum circuits. So data is the equivalent of these qubits that I've been talking about, and that I will define more precisely in a minute. Then we have operations that we perform with unitary transformations, which are the quantum gates that we have in these circuits. And then in order to obtain results, we need to measure the value of these qubits. Okay, so let me explain a little bit what is each of these elements in detail, in order to understand a little bit better how to program a quantum computer. Okay, so the first thing that we need to mention is that quantum information is stored in what we call quantum qubits or quantum bits or qubits. As you know, classical bits can only have two different values, either 0 or 1. So this is a discrete quantity that we use in order to make computations with our classical computers. But quantum bits can take an infinite number of values. They can be a superposition, they can be a combination of both 0 and 1. Mathematically, this can be expressed as a vector which lives in a vector space, a Hilbert vector space, in which you have a basis of two elements. These elements are the equivalent of the classical 0 and 1, and we usually denote them with this funny looking notation, which is called the Dirac notation. This is what we call a ket, and it's nothing else than just a vector. So we have an orthonormal basis here, with one of the elements of the basis being this 0 and the other element of the basis being this 1. And a general qubit can be in a state which is a linear combination of these two elements of the basis, with just one restriction. These alpha and beta are complex numbers. And for this to make sense, we will see in a minute why physically we need this condition. For this to make sense, we need that the absolute value squared of these complex numbers add up to 1. Okay, but since these are complex numbers, we can have an infinite number of different combinations of these qubits. Why do we need these values to add up to 1? Well, this comes from the fact that when we need to observe, when we want to know what is the value of a qubit, we need to perform a physical measurement. And when we perform a physical measurement in a quantum system, as you know, the system collapses. So in fact, although theoretically you can have infinitely many values for these qubits, when you measure them, you always obtain either 0 or 1. You don't obtain an infinite spectrum of values. You obtain just 0 or 1. And in fact, the probability with which you obtain either 0 or 1 depends on the coefficients alpha and beta that form this combination, which is the state of the qubit. And in fact, you will obtain 0 with probability, which is exactly the absolute value squared of alpha, and 1 with probability, which is the absolute value squared of beta. And this is why we need these two quantities to add up to 1, because they are probabilities, and you either measure 0 or 1, so they need to add up to 1. So, well, this is something that is quite different from what we have in classical computing. In classical computing, we have just one bit with one value, either 0 or 1. And when we observe this value, well, it's always 0 or it's always 1. We don't have a probability of obtaining one value or the other, okay? What is more, in quantum computing or in quantum physics in general, when you measure a system, it collapses to one of these states. And then if you measure again the system, then the system is now in whatever state you had measured before. So it has collapsed. It doesn't recover this state with alpha and beta. Okay. So if you want to know what is the value of alpha and beta, it is not just possible to measure this state once and again in order to obtain a better approximation of alpha and beta, because it has collapsed and it's 0 now or it's 1 now. Okay. Well, you could think that maybe you can overcome this problem by not measuring the state directly, but first making a copy of this state and then measuring the copy. Okay, and then you can repeat this several times and obtain the value alpha and beta. The problem is that it is quite easy to prove mathematically that this is not possible. This is what we call the no cloning theorem. And this is again a property that is very different from what we have in classical computing. In classical computing, you have data and you can copy this data as many times as you want. In quantum computing, in quantum systems, if you have an unknown state, if you don't know what is the state of the qubit, there is no physical way of copying this information in an independent qubit in order to have some backup of the information that you have there. And this will have also some consequences for the way in which we design quantum algorithms. Okay, so this is what we have when we deal with just one qubit, but of course, the most interesting thing happens when we have more than one qubit. So imagine that you have n different qubits, and of course, each of them can be in state either 0 or 1, so you have a lot of different possibilities, 2 to the n different possibilities. They can be in 0, 0, 0, 0, 0, 0, 0, 1, and so on. But this being a quantum system, it can not only be in one of these possibilities, but it can be in all the possibilities, a combination of all the possibilities at the same time. Okay, so the general state of n qubit system is a combination of all these 2 to the n possibilities. So now we are working with a vector space, a Hilbert vector space, but the dimensionality of this Hilbert space grows exponentially with the number of qubits. And as we will mention afterwards, this is one of the most appealing things about quantum computing, that you can work with naturally with an exponential number of states with just n qubits in your system, okay? And again, you have this normalization condition, because when you measure a system with n qubits, again, it collapses to one of the possibilities, 0, 1, 0, 0, 1, 1, 0, whatever, with probability that is exactly the absolute value squared of the coefficient that expresses the state of the n qubit system. Okay, so again, we need this normalization condition. Okay, so we know now how to have data in a quantum computer. We have this information stored in the state of the n qubit system that we have. We know how to obtain results. We need to measure, and this will collapse the state to a certain configuration that we can read. But we still need to know how to operate on this information, how to transform this operation, how to make computations with this operation. And the thing here is that, again, we are dealing with a physical quantum system, and the only transformations that we can impose on quantum systems come from the solutions of the famous Schrödinger equation. And this equation is linear, so it has solutions that are, in fact, linear transformations. In the setting of a finite number of qubits, which is the one that we are considering with this quantum circuit model, linear transformations are, of course, matrices. And these matrices have interesting properties. They are not any kind of matrix. They are what we call unitary matrices. And they have this property that they are matrices of complex numbers, whose inverse is obtained by taking the dagger of the matrix, which is nothing else than the conjugate transpose of the matrix. Okay, so we have this linear transformation given by a matrix, and the inverse of this linear transformation is just the conjugate transpose of the matrix. This has very important consequences for the way in which we operate with quantum information. For instance, any transformation that we do on quantum data, as long as we are isolated from the environment, is reversible. So this is something that we do not have in general in classical information processing, because most of the operations that we do on classical data, for instance, when we compute the AND of 2 bits or the OR of 2 bits, these operations are not reversible. Okay, so this is something that is again different from what we have in classical computing. Okay, any of these possible solutions to Schrodinger's equation is what we call a quantum gate. Is what we call a quantum transformation of this of the state of these qubits. But of course, not all of them are so easy to implement in practice. So in practice, when we have a quantum computer, like one of these computers created by Google or IBM that I showed you before, we only have access to a certain number of these unitary transformations. And in fact, we can prove mathematically that this is not a limitation, because when we have a certain number of these transformations, we can generate all the others or approximate all the others as much as we want. And usually we work with just a subset of all the possible transformations, and then we work with just 1 and 2 qubits, and from these operations we can compose all the operations in an arbitrary number of qubits. Some of the most important quantum gates include the X or NOT gate, which just takes a 0 to a 1 and a 1 to a 0, and of course a combination of these values. It's taken to again a combination of the negation of 0 and the negation of 1 by linearity. We also have this Hadamard gate, which is very important because it allows us to create superposition, to create from a state which is in state qubit which is in state 0, we can create a state that is in a superposition of 0 and 1. We also have these phase gates, and we also have this control NOT gate, which is very important because it allows us to create entangled states. Entangled states are states in which the description of the whole state cannot be simplified as or described as information in just one of the qubits and another qubit. Okay, so it cannot be factored into information, independent information on one qubit and another qubit. And this is something that is also particular to quantum computing. In classical computing, we don't have this kind of behavior. And this is very important for many quantum algorithms and for quantum cryptographical protocols that use this property, for instance, to securely distribute cryptographic keys. Okay, here I have shown you, I have listed some of these some entangled states which are very important in quantum information theory, which are called the Bell states. And the important or the striking properties of these entangled states is that when we measure one of the qubits, for instance, if we measure this state here and the first qubit is seen to be in state 0, then the whole state collapses to this 0, 0, and then without the need of measuring the second qubit, we know that it is also in state 0. Okay, and this is a special property that we can use to develop some cryptographical protocols and some other important quantum algorithms. As I've mentioned before, we don't need to implement each and every possible quantum transformation, but we can create them, we can compose some subset of these transformations in order to obtain any possible transformation to the level of approximation that we want. Okay. Again, another thing that is important in quantum computing, and that is probably a little bit different from classical computing, is that here we have a continuous range of values. We don't have discrete values, and this can have serious consequences when we try to preserve the information. One of the things that was developed at the beginning of quantum computing was a theory of how to correct quantum errors that can occur because, for instance, we don't apply the quantum gate exactly as we want, but we have a small error in this application, or we have some influence from the environment. Okay, and in this situation, we need to be able to correct the information to restore the state to the correct value. This seemed to be a very difficult thing to do at the beginning of the development of quantum computing, because, as we have mentioned, when we have a quantum state, in order to see what is the value that is stored in the quantum state, we need to measure it. And when we measure the state, it collapses to a certain state, and we lose all the information about this superposition of states that we had at the beginning. But fortunately, there are ways, there are what we call quantum error correcting codes that allow us to prevent this corruption of the information when we have certain conditions about the possible errors that can occur in our quantum computer. So, as we have seen, this idea of processing information with quantum computers is similar in some ways to the classical computation that we do with classical information, but it also has some particular properties that makes it quite different. At the end, we are just multiplying matrices with vectors, because the information that we have in these qubits is just a vector in a Hilbert space, and the transformations that we are doing with this information come from linear transformations. Okay, so you may think that, well, this is just a particular case of what we have in classical computing. And in fact, it is so, and this is why we can prove that anything that we can do with a quantum computer, we can also do with a classical computer. But of course, the thing here is that the size of the dimension of the Hilbert space in which we are working, in the vector space in which we are working, grows exponentially with the number of qubits. And this becomes very rapidly difficult to simulate with a classical computer. So this idea of having the possibility of dealing with an exponential number of parameters in our quantum state is what gives some of the power that we find in quantum computing. This is not the only property that makes a quantum algorithm faster than a classical algorithm, and this is something that you may have read in popular descriptions of quantum computing. And it's sometimes said simply that, well, a quantum computer is faster or is more powerful than a classical computer because it can explore all the possibilities in parallel. It explores an exponential number of possibilities in parallel, and then it finds the answer to any problem immediately. Okay, So the answer or the thing about this popular conception about how quantum computers work is that it has some truth to it, but it's not all the truth. So if we consider an implementation of a Boolean function, for instance, or a classical function in general, we can implement this with what we call an oracle. It's just a way of creating a reversible version of this classical function. And then, since this is a quantum circuit, we can use the possibility of creating a superposition of all the possible states, of all the possible combinations of zeros and ones in our qubits. And then we can apply this function to create a state in which we have evaluated all the values of the function, all the exponential number of values of the function, with just one call, with just one application of this quantum circuit. And in this situation, we have all the information about the results that this function gives on all possible inputs. The problem is that, well, we have the information there, but now we need to access this information. And in order to access this information, of course, we need to measure the state. But when we measure the state, we obtain just one of the possibilities. So we obtain, in fact, at random, one of the values of the function. So we have evaluated all the values of the function, and we have all of them in this superposition. But when we try to access this information, we just recover one of them. So we have gained nothing. Only by using this superposition, we gain nothing. What we need to add to obtain a quantum algorithm that is useful is not only this superposition and this entanglement that we have here, but also the third element that I was mentioning at the beginning, also this interference. So what we can do, or what we can try to do, because it's not so easy, is to manipulate the amplitudes, these coefficients that we have here in these combinations of all the different evaluations of the function. So some of them annihilate others, and some of them grow bigger when we annihilate some of the other amplitudes, in order to increase the probability of obtaining the desired result. And this is what we do in any of the quantum algorithms that are used in these applications that I was mentioning at the beginning. This is the idea of using not only superposition and entanglement, but also this interference in order to make obtaining our solution more probable. This is, for instance, what we do in Grover's algorithm, which is used to search in an unsorted list of elements. And with this idea that is used in Grover's algorithm, which is called inversion about the mean, or more general, this gives us something that is called amplitude amplification. What we do here is to exploit this possibility of increasing some of the probabilities and decreasing others in order to obtain a quadratic speed up in search in unsorted listed of elements. So for instance, if we have 1 million elements, and we are looking for a particular one, but the list is not sorted, in a classical setting, we need to check in average half of the list in order to find the one that we are looking for. But with Grover's algorithm, we can find with high probability the element that we are searching for with just 1,000 queries to the list. Another algorithm that uses this idea of interference together with superposition and entanglement is Shor's algorithm, that is used, as I've mentioned briefly at the beginning, to factor big natural numbers. and has strong consequences for some cryptographic protocols. And the idea here is that we use these quantum computers for a particular step in a factoring algorithm. So this is, I'm not going to explain every little detail in this algorithm, but I want you to know at least that most of these steps are done in the classical computer, and then this part here, which is hard for the classical computer, is delegated to the quantum computer. And the quantum computer, using something that is called the quantum Fourier transform, is able to obtain this period here, this order here that we need in order to factor numbers. So again, we have this idea of having different amplitudes and annihilating some of them in order to make one of the solutions more probable. And then when we measure the state, we obtain back the solution that we need. These algorithms and others that have been proposed for other problems, like the HHL algorithm for solving systems of linear equations, work perfectly on paper, but are still impossible to be implemented in the quantum hardware, in the quantum computers that we have today. These algorithms require that we have a big number of qubits, and that these qubits preserve their properties for quite a long time, and also that these operations are protected against noise and against errors. Okay, so this is something that the community is working in order to obtain quantum fault-tolerant computers, but for now we only have what we call noisy intermediate scale quantum computers, which are computers that are subject to noise, which have a limited number of qubits on the order of several dozens or so, and that are not fully connected. For instance, this entanglement that we need to create in some of the algorithms cannot be done with any pair of qubits that we have in the circuit. Only with, for instance, those that are close to each other. Okay. Despite this, we have been trying, the community has been trying to apply these limited quantum computers that we have today in different areas. And for instance, we can use these quantum computers in quantum chemistry or quantum physics simulations, in optimization, in machine learning. And although we have not yet been able to use these quantum computers in a practical problem with more efficiency than a classical computer, as you know, we have achieved what is called quantum supremacy for certain tasks, which are not especially relevant in practice, but that are not feasible to be done with classical computers. And just to wrap up, what can we, or what do I expect from quantum computing in the future? Well, of course, what we need is first to obtain more evidence of the advantage of quantum computing, even in these particularly interesting tasks, but at least to show that quantum computing can be faster than classical computing in some tasks. Also, we need to explore more this possibility of practical applications with the quantum hardware that we have today. We also need to make advances in the technologies for the implementation of qubits in order to have the possibility of creating computers with more qubits, more stable, protected against errors, and with longer coherence times. And of course, from the theoretical perspective, we would like to have new quantum algorithms which offer speed ups over classical algorithms, if possible, exponential speed ups, with the final goal of having a lot of different possibilities of applying quantum computing when we reach the stage in which we can have fault-tolerant quantum computers. Here, for instance, I'm showing a picture of an application of quantum, these noisy quantum computers to chemistry simulation. This is back from 2016, but there are many developments in this area to in order to obtain practical applications of the devices that we have now. And just to finish, some spam, if you allow me. If you want to learn more, I taught an online course on quantum computing from CERN last year in November and December, and you can find the recording of the lectures on CERN's YouTube channel if you want to know more. Thank you for your attention, and I would be happy to answer any question that you may have.
Thank you very much for the presentation, Elias. I'll be taking the Q&A session. It was really cool. Well, if any participant has some questions, please let us know, and we will well invite you to pose the question yourselves. But I can start with a comment and also with a question. The comment would be to strongly recommend this series of lectures that we are still seeing in the slide. So myself, I took most of them. In honesty, I was not yet able to find the time to see them all, but yeah, that they were really instructive for me. So I really do strongly recommend following those. Okay, and my question, and yeah, I'll give the word to Lei. Lei, do you want to ask this question yourself? Let me try to find you in the list. Yeah, I will invite. Well, maybe I can try to unmute. Lei, do you want to ask the question yourself? Yes, please go ahead.
Of course, thank you. Thanks for the talk. I enjoyed it. So if we can go back to your previous slides when you compare the different types of quantum computers, we have these, superconducting quantum computer and so on and so forth. Could you please elaborate on those different types and, give a brief comparison among them?
Yes.
What are the pros and cons? Which one, is winning, maybe by a margin? And in terms of noisy levels, what are the differences? Is there any advanced technologies on that? Thank you.
Okay. Yes, sure. Well, I must say that I'm not a specialist in the physical implementation of quantum computers. My expertise is mainly on quantum algorithms, but I can at least mention that, for instance, superconducting qubits have this problem of needing very low temperatures and needing to be isolated from the environment in order to preserve coherence and quantum properties. But they have the advantage that they use the kind of technology that we use to build classical computers. So this is something that we know how to do fairly well. So this technology is more advanced than the others because it can piggyback on the developments of classical digital computers, okay? But probably this technology will be overcome by other technologies for implementing qubits. For instance, trapped ions are much more stable than superconducting qubits, and the operations that you can do with them have lower errors. Okay, and also you can entangle these qubits more easily than what happens with superconducting qubits. The problem with them is that they are more difficult to scale. It's more difficult to construct a quantum computer with a lot of quantum of trapped ion qubits. I think that the biggest quantum computer with this technology up to this moment is about 12 or 15 qubits or something like that, while we have superconducting quantum computers with up to 70 qubits, which is quite a lot more. But this is a technology that is it's been developed and has been seen some advances in the past few months. Okay. Another technology that is quite interesting but has some problems is the technology that is called the topological qubits. That is being investigated, for instance, by Microsoft. They have invested a lot of money in investigating this technology. And the good thing about topological qubits is that they are protected against error. So you don't need to use these quantum error correcting codes. The problem is that they are based on some quasi-particles that are supposed to exist, but nobody has found them yet. In fact, there was one paper in which some evidence of the existence of these particles was shown, and it was retracted a few weeks ago because there were some problems with the experimental methodology. Okay, so well, this was very promising, but up to this point we have 0 qubits, no qubits. Another technology that is not mentioned here that is also very promising is the one that uses photons in order to implement qubits. And in fact, you may have heard that back in November or December, some researchers from universities in China obtained also quantum advantage or quantum supremacy with a photonic computer. And the good thing about this technology is that it's quite easy to implement operations on individual qubits with photons and to store information in them. But the problem is that it's quite difficult to make them interact. They are more protected against the noise from the environment because photons interact very rarely with matter compared to other technologies. But the problem is that you need to make them interact in order to create entanglement, for instance. So this is a problem. So each technology has some advantages and some problems. Hopefully, one of them will be able to overcome the difficulties and give us the possibility of creating scalable, fault-tolerant quantum computers.
Thanks for the answer. If you have any further questions, please just write them down. I will also be posing the question I promised earlier. So I think I will stay in this, in asking for your opinion in terms of, say, comparing pros and cons. But I would like, please, to ask you to focus in the computation models, okay? And my question is like the following. So, say in classical, and yeah, again, it's I think it's natural for us to try to compare what we already know from the classical world and try to say, yeah, take that as input to see what we can do in the quantum world. And computation models, so the natural way to think of, say, a classical computer executing is that of a program that has an auxiliary memory that can be changed and then can be taken as input to, well, support running computations and then producing results. But this does not seem well, easy or if at all possible in the quantum world. Can you tell us a bit what you think this means for quantum computing? Will we really need, say, an alternative to a memory to reach practical impact?
Well, this is a big problem in the application of quantum computing, because these models, of course, are mathematical models, and you can prove that, for instance, this HHL algorithm works under certain conditions faster than the classical algorithms that we know for the same problem. But then you have the problem of how to interact with classical data, okay? And how to make different quantum algorithms interact with each other, okay? So in that sense, for instance, these models allowed you to compose programs whenever the output of one program is quantum and the input of the other program is quantum, okay? But this is something that in practice you rarely have. You can have, for instance, quantum sensors that produce quantum data that you can already use with a quantum algorithm, but this is just one particular situation. The most common situation is that you have classical data and you need to somehow give it to the quantum computer and then recover classical information in order to know what is the answer. And for that, we need, as you mentioned, some form of quantum memory. There are several proposals of quantum RAN devices, but we don't know how to implement these theoretical proposals in real devices, okay? So this is one limitation. This is something that we need to address. For instance, what we are doing with this model of, or with these NISQ quantum computers that we have today, is to use them as quantum accelerators in the same way that you have a GPU, for instance, or a TPU, which works well for certain particular problems, but you wouldn't use a GPU to run an operating system. You would use a GPU to make matrix computations. You can use a quantum computer to solve particular problems. And then you interact with the classical computer in a limited way. For instance, with what we call variational forms, in which the operations that we do with the qubits are the parameters of these operations are the input provided by the classical computer. Okay, so we separate the two worlds, the classical world and the quantum world, and we create a very clear interface between the two worlds. And we delegate, like in Shor's algorithm, for instance, just one task to the quantum computer, the task that it is able to accelerate. And this is what I see happening in the near and medium term, until we have computers that are able to hold quantum information for a longer period.
Okay. Do you think it's, if I may ask one more,
Yeah.
do you think it makes sense to think about the current state of quantum programming in terms of, say, more or less stateless functional programs, like you don't have side effects and like you're just sequencing operations and
yes,
results?
I think it makes a lot of sense. And in fact, this quantum circuit model, somehow it's kind of a functional description of the operation of the quantum computer, because you start with a known state, and then you apply gates which operate on the output of the previous gate, and you compose these gates in order to obtain the final result. The main difference is that you cannot easily compose, for instance, these different quantum circuits, because you always need a quantum measurement. And this quantum measurement somehow breaks this dream of quantum information and the communication between one part and the other. But up to that point, if we eliminate the measurements, then what you have is something that is purely functional, without side effects, and without interaction with the environment, or without input output or something like that.
Okay, so great. Yeah, great. Thanks again. Thank you for the answers. So I guess there are no further questions, and I guess we are also a little above the hour. So I would again like to thank you very much for this so interesting talk, okay, and for your availability to join us. And also, I would like to thank all the participants who attended today. Your presence is, of course, important for the talks as well. And so I wish you all, say, a very nice day wherever you are, and all the best. And thanks again, Elias. It was very kind of you. Okay.
Thank you. Thank you. It was my pleasure. Thanks.
Thank
Bye.
you. Bye-bye. Cheers.